Good day, everyone. My name is Oda Lutz, and I'm coming to you from NASA's Jet Propulsion Laboratory in Pasadena, California. I am your host today for the Scientist for a Day Ask the Scientist event. A lot of you submitted essays to the Scientist for a Day essay contest, and we really enjoyed reading your arguments, your scientific statements. You all did a wonderful job, and we really appreciate your interaction. To get started, we are going to take a reminder look at the Scientist for a Day video that Bethany Epic did for us to introduce us to the program. So if we could go ahead and run that, that would be lovely.
Welcome to the NASA Scientist for a Day essay contest. I'm Bethany, and I'm an engineer at NASA. The topics of this year's essay contest are 3 mysterious moons that orbit the planet Uranus: Ariel, Oberon, and Titania. Your assignment is to learn more about these mysterious moons and decide which one you would explore first in a potential future robotic mission to the Uranus system. Enjoy exploring, learning, and discovering. Have fun, and good luck.
Awesome. Thanks so much, Bethany, for giving us that introduction. And I want each of our panelists today to introduce themselves. And Bethany, I'm going to go ahead and start with you. I know we're having a little bit of video problems, but hopefully your audio will come through. And hey, there you are in video. Awesome.
Hi. Well, the video seems to be frozen, so I probably will leave it off for most of the time. But hello, everybody. I'm Bethany Eppig, and I am the Radioisotope Power Systems Programs Office NEPA and Launch Approval Manager. And what that means is that I help missions that use radioisotope power systems to get approval to launch by meeting environmental and flight safety requirements. And I'm stationed at the Glenn Research Center in Cleveland, Ohio.
Fantastic. Thank you so much for that introduction. And now we'll move to Kelsey. Kelsey, what can you tell us about yourself?
Hi, I'm Kelsey Singer. I'm on the New Horizons mission, which also uses a radioisotope power source. And I see Deepak has a beautiful model in his office of the New Horizons spacecraft, so that's great. And I do a couple of different roles on the mission. I get to help plan the observations that we take, like the pictures and the other kinds of data. And I also get to play with the data when it comes back, which is great. So I do geology and geophysics, but just not on Earth, on other places in the solar system.
Super. That sounds like interesting work. Gosh, both of you have interesting jobs. I'm looking forward to hearing more from you today. And Deepak, what can you tell us about the work you do and yourself?
Hi guys, I'm Deepak. I work at the Johns Hopkins Applied Physics Laboratory, and I've been here for about 20 years, and I'm an engineer, like Bethany, and I've had the opportunity to work on lots of missions all across the solar system, including New Horizons, as well as some others that we're going to talk about today. Right now, my main mission is actually the Europa Clipper mission. I'm the telecommunications manager for that mission, so I make sure that the spacecraft can talk to Earth once we launch. So I look forward to talking to you guys and answering a lot of questions. This will be a lot of fun.
Yeah, I think this is going to be a great time. And we have such wonderful experience among our panelists. And I want to give a big shout out to the NASA's Radioisotope Power Systems Office that sponsored this year's Scientist for a Day competition. We really appreciate that support, and I know the students do as well. The RTGs are really fascinating technology, and we even have some questions about those today. So we're going to start out, though, with some questions about the targets that were the subjects of this year's Scientist for a Day contest. Our first question comes from one of our U.S. contest winners. Aaron Heisel from Helena, Montana asks, are there plans for another mission to take more pictures of Oberon or any other of Uranus's moons? And if so, what do we hope to discover? And I believe Bethany, you wanted to take that one?
Yeah, and Kelsey and Deepak, feel free to add more. But what I would like to say is that I'm currently unaware of research that's specifically for Uranus, and that's why we needed your guys' input for these essays, right? But there are 2 possible future missions in competition to research distant moons. They're just not specifically for Uranus. So one is the Io Volcano Observer, and you can look that up online as well, but It would explore Jupiter's moon, Io, to learn how tidal forces shape the planetary bodies. Io is heated by the constant crush of Jupiter's gravity, and it's the most volcanically active body that we know of in our solar system. So that's a really interesting potential future mission. There's also the Trident mission coming up. So potentially, right? So these are maybe missions that we'll have in the future. So Trident would explore Triton, which is a unique and highly active icy moon of Neptune, right? So Neptune Trident, so that's a nice name, to understand pathways to our habitable worlds at tremendous distances from the sun. So NASA's Voyager 2 mission showed that Triton has active resurfacing, generating the second youngest surface in the solar system with potential for erupting plumes and an atmosphere. So both of these are currently in competition, and we can't wait to see what future down select missions might have for us.
Awesome, thank you. And of course, as scientists, we'd love to have all of those missions that are in proposal stage be funded, and then we could go explore all these interesting places. There's so much to explore in the solar system, so be really, really cool to get some of those funded. Our next question is from another one of our US contest winners. Ramesh Patar from Frisco, Texas asks, if Titania does have a subsurface ocean, then how deep would it be? Anyone?
I can take a crack at that. So I will also add to Bethany that there are some missions. People would love to go back to the Uranus system, and there are some missions in the very early stages of being planned and thought out. They have not yet been submitted, but I really think that it's possible that could happen in you guys' lifetime. And you could be on those missions. So this is actually a great time to be learning about Uranus and their amazing moons. So one of the reasons that they're amazing that you guys just brought up is that there's this possibility of having what we call a subsurface ocean, which just means that the ocean is not on the top of the body like our beautiful ocean is on Earth, but that it's under a layer of ice. And I will freely admit that I have not looked these numbers up specifically, but I know that for these size moons, it would probably be tens to hundreds of kilometers down. So we don't know yet, and we would love to go back and find out.
That's one of the trickiest things about exploration is, I mean, we want to explore because we don't know, but we don't know. So it's hard to figure out what kind of, how far we'd have to go down and what kind of instruments we need to take. But it's all part of the scientific process, which is cool. Another comment? Okay.
Oh, I was just going to add that, you know, there are a couple other missions that are currently in development. I know the question was asking, are there future missions? The ones that Bethany alluded to were missions that have not yet been selected. However, there are 2 missions that are in work that are going to be exploring some of these ocean worlds. These ocean worlds are really, from my point of view, the most fascinating parts of our solar system right now. Because as Kelsey mentioned, you know, there's these entire ecosystems of water encased in ice, and they're old. They've been there for billions of years. They've been interacting with all the various chemicals that are on the moons themselves, and there's energy from, you know, the sun's energy input, as well as when these moons are orbiting either Jupiter or Saturn or Uranus, wherever. There's these tidal forces that are crushing the moon. So you have the right ingredients. You have water. You have energy. You have time. These are all the ingredients to how life evolved here on Earth. So that's why I'm really excited to be a part of a lot of these missions that are exploring these things. And we hope you guys join us in this journey as you guys get older.
Yeah, it seems there is quite a lot of water out there.
And to just give you guys an idea, so Europa, that's we're building the Europa Clipper mission right now. And we think that Europa has twice as much water. Imagine all the water here on Earth, like all the oceans, every bottle of water that you have, every ocean, every waterfall, and then double it. That's how much water we think is there on Europa. And like I said, it's old. So you can only let your imagination go and try to figure out what do you think we could find there once we get there. And that's why we do these things. We need to figure that out.
Yeah, that's going to be one really amazing mission to follow. It's Europa is it's really a neat place. I like to say it's a cool place because yeah, it's cold, but it's really a neat place.
It's a cool place that we would love to dive into. I'm sorry for that pun to him.
Yeah, for sure, for sure. All right, so our next question comes from another one of our US contest winners. Stephanie Dragoy from Washington, D.C. asks, how difficult would it be to map Ariel and land a probe on this moon during the same mission?
Do you want me to jump in really quick, or
Go for it.
So I'll speak from an engineering standpoint, and then Kelsey, maybe you could back
Sure.
me up as well. The answer is very tough. So one of the most tricky things about going to the outer planets is slowing down, right? So we spend all this time speeding up to get out there because these things are far away. It took us 9 years to get to Pluto. And that's because we did everything we could to get there as fast as possible. 9 years. Imagine that. It's a long, long, long time. But we were operating at full throttle as we did our flyby. If we were to have to slow down and actually get into orbit around a moon to actually map it, like you were saying, or slow down sufficiently that we could actually land on it, we would have to start slowing down about halfway through the journey as opposed to like right at the end. It's not like you're driving a car and you can just hit the brakes right away and stop. You need to slow down over time, and that'll increase the length of your journey by decades possibly. So it's right now a lander at a moon that far is probably beyond it'll require more fuel than we could launch at this point in time. So very hard.
Well, I totally agree with everything that Deepak said. And I was just thinking that instead of orbiting the moon itself, we do have the technology to orbit Uranus, the giant planet nearby. Yes. And we've done that successfully many times. We've done it at Jupiter, we did it at Saturn, and I think it's Uranus this time. But that works by you fly by the moon while you're orbiting the planet, and you can get lots of different pictures that way. And you can even drop something off sometimes. So I still have hope for a lander on Ariel.
Yeah, that would be really cool. You could do something like the Cassini mission did with the Huygens probe landing on Titan. So
yes, exactly.
Yeah, lots of cool options. So we're switch planets over here for a second. One of our other U.S. contest winners, Annie Hu from Solon, Ohio, asks, based on the accomplishment of the Ingenuity helicopter achieving controlled flight on Mars, what does this mean for the future of Mars exploration, and how will future technology like this help us learn more about Mars? Bethany, you want to give that a shot?
Well, I saw Deepak raise his hand there, so I'll just let him go ahead.
I'll just give a couple quick tidbits. So Mars, as you guys know, we've explored a lot with rovers, and Mars is very conducive to using rovers. Mars has a very, very thin atmosphere. And because if you want to fly with a drone or a helicopter, you need air, obviously, because the blades have to push against that air to get flight. Because Mars has a very thin atmosphere, it's very hard to actually fly on Mars and fly something that has any sort of weight to it. Now, Ingenuity, fantastic accomplishment, but it's a very light probe. And if you want to have like cameras and spectrometers and all sorts of other scientific equipment, that probe will start to get heavier and heavier. And that makes flight really difficult on Mars for a sizable object. That's why right now I think using the rovers is probably the best way to explore Mars. That being said, Bethany mentioned Dragonfly earlier. Dragonfly is a mission that we're working on that we're hopefully going to be launching in 2027. And that is going to land on Titan, which I think is probably the most exciting place in our entire solar system. And Titan, in contrast to Mars, has a very thick atmosphere. It's almost, I think, 4 times thicker than here on Earth, as well as the gravity on Titan is about 1/7 that of Earth. So it's really, you're really light and there's a lot of air. And basically, if any of us actually stood on Titan and just flapped our arms, we would probably fly ourselves. So we are going to be flying and on other planets, other moons, and Ingenuity was our first time actually doing that off of this world, and that technology is going to be useful as time goes on in other locations.
Cool. Yeah, that Dragonfly mission is going to be something, isn't it?
It's going to be awesome.
Yeah, definitely. If you are not familiar with the Dragonfly mission yet, take a look at that. You can find some information on the internet. It's really an interesting idea, and I'm looking forward to it. We have another question about Mars. What is the next step NASA is trying to take to further explore Mars after their accomplishment of landing Perseverance and Ingenuity?
I'm happy to take this one because I actually was fortunate enough to work with the team before I joined RPS. So the Mars Sample Return is a proposed mission to return samples from the surface of Mars back to Earth. So that's extremely exciting. This mission would use our robotic systems and a Mars ascent rocket to collect and send samples of the Martian rocks, soil, and some atmosphere all the way back to Earth for detailed chemical and physical analysis. This mission is being planned jointly with the European Space Agency, and Perseverance is currently conducting scouting for this potential future mission. So NASA Glenn Research Center is working on specifically a new type of tires for this mission. So this is what I worked on before I joined the RPS program, and that's called the Mars Spring Tire, which uses shape memory alloys. These tires are made from a shape-shifting material that give you an unmatched durability, right? Because you don't want to get a flat tire when you're on a different planet. So they can actually envelope rocks without the risk of puncturing. And they're designed to also help you provide a smoother ride, almost like adding some shock absorption. And this is going to minimize potential damage to systems on the rover itself. So this is a very exciting future opportunity with Mars, and I can't wait to see what they bring back and what that data gives us.
Yeah, it's that Mars Sample Return mission is going to be really neat. And I am so intrigued by the wheel research that's going on. I'm so glad you brought that up because, and it's neat to know that you worked on that. That is some really, really cool technology. I haven't read all the stuff on it, but it sounds like it's really neat. We're going to shift gears a little bit here. We had a lot of questions about the RTGs, the radioisotope thermoelectric generators. And so I'd like to take some of those and just kind of go over some of the basics. And Bethany, in your intro video, you referenced them as a sort of battery. So there's a lot of questions about them as a battery. So want to kind of throw out a couple of questions and then let y'all take whatever ones you'd like. One of the questions is, how are RTGs made and what radioactive substance are they made of? And could you use them on Earth? And then another is, how long could a battery like that work? So that's a little smattering of questions. Bethany, do you want to give that a shot?
Yeah, I'm happy to start off, and you guys are welcome to add anything else in. So we'll start with how are they made and what radioactive substance are they made of. Radioisotope power systems use the heat produced by the natural decay of plutonium-238 or Pu-238, and they generate electricity to operate the spacecraft systems and the science instruments. Now, we have a very strong partnership with the Department of Energy in this. So the Department of Energy actually produces the plutonium-238, and they work with NASA to provide the RTGs to support the NASA missions. The plutonium-238 is very different from the material that is used in nuclear weapons, and it can't undergo any type of uncontrolled chain reaction. So I want you guys really just think of this as a big heat pellet. You know, this isn't something that is nuclear in the other ways that you're probably thinking of. Now, while RTGs could work here on Earth, NASA really chooses to only use them to enable our space missions to some of the most challenging destinations in the universe where other power options really aren't readily available, right? So when you're going that far out, you don't have the options for solar power as a reliable energy source. They also don't have any moving parts, which makes them extremely reliable, right? So you have less potential for anything breaking when they're that far away from Earth. And then I think the second question was, do they run like normal batteries? Was that what you asked?
Yeah, a couple other questions. One is, how are they made exactly? And then how long can it work?
Okay, let me hit on the how long can it work. So what we can think about is, well, how it's made, we fuel the MMRTG in partnership with DOE, and at that point it produces about 110 watts of electrical power. So when we're using them, they're giving off that heat by the natural decay, and there's the coldness of space. So it's using something that's called the Seebeck effect, which is a property of physics where you can have a large temperature difference, and it's applied across this conductive material that's very special to the RTG, and it creates your electric voltage, or your generations of, electricity. So once it fuels, the power does stay on, and it can operate. We designed them to operate for a minimum of 17 years. So 14 years at least for the mission and 3 years before launch. But our experience has showed that they last much longer, like in Voyager 1 and 2, that have been lasting for almost 44 years.
So yeah, so what Bethany said is completely correct. They can last for a long time, but what happens is that it's, as she said, the electricity is made by the decay of these molecules that are of the fuel, and it's decaying. As soon as it's made, it starts to decay. So with every passing year, you might start off with roughly 100 watts, but then a year later, you might have like 98 watts available. And another year later, you might have 96 and then 94. So over time, it just kind of gets lesser and lesser and lesser in terms of how much energy it can produce, how much power it can produce. So in terms of how long you can use it all the way until it doesn't have any power left. It's kind of like a battery that you use for anything at home. It's just that at some point in time, it's just not generating enough juice to do anything with. And so that's, if we look at New Horizons, for instance, that's the spacecraft. Right here is the RTG, and it looks a lot like the RTG that you're seeing on your screen. And right now, as we speak, it's flying. It's past Pluto, it's past Arrokoth, it's in the Kuiper Belt right now. But with each passing year, it's getting less, and it has less and less power. It's producing less and less power. And sooner or later, it's not going to be able to produce enough power to actually transmit any signals back to Earth. That's probably going to happen in about 12 to 15 years or so. So that's basically what limits your lifetime, is how much energy does your spacecraft need versus how much energy does the RTG produce.
And Deepak, I know with Voyager being old, very old, past that 17-year lifetime, it's still transmitting data and it's still operating some of its instruments. But as the power supply has dwindled, we've had to make some tough choices about turning off particular instruments because you can't run them all. You don't have enough power. Is the same thing happening with New Horizons?
Not yet. So right now that it's still able to operate, and I think Kelsey could probably jump in. She's on the operations team. My job on New Horizons ended at launch. I got it up to launch, and then I handed it off to folks like Kelsey to do great things with the great thing that we built. So
well, thank you. We needed that. We needed to get it to launch. Yeah, no, that's a great question. And we right now we don't have to turn anything off. But as Deepak and Ota were saying, the power is slowly declining. And at some point we will not be able to get a signal back from the spacecraft, which will be a sad day for all of us. But the spacecraft will keep on going out. It's kind of headed out of the solar system. It's not traveling quite as fast as the Voyagers, so New Horizons will not catch up to the Voyagers. But it's going to go on a similar type of out of the solar system direction.
All right, interesting. That New Horizons is going to be another one of those long-standing spacecraft, and that's going to be really neat to see what we get from that mission. Question about the Mars missions: are there any RTGs or other radioisotope power systems being used on any of the current Mars missions?
I'm happy to answer that about Perseverance. So there is one RTG on the Perseverance rover. And since the Perseverance rover uses the excess heat from the MMRTG to warm the rover, it doesn't need any other type of RPSs just for heat. So we also have some RPSs where they're called radioisotope lightweight heater units, and you just kind of put them over your spacecraft to provide light heat.
All right, very good. And yeah, Curiosity, the Perseverance predecessor, also has an RTG. And those RTGs are really good for powering the multiple science instruments that are on board, and we don't have to worry about a darkening sky at night or a dust storm. The RTG just keeps on putting out that heat, which powers those spacecraft. So that's really useful. Another question about RTGs: are there any upcoming or current missions? We've got the current ones on Mars, but others that are or will be using RTGs or other radioisotope power systems?
Yeah, so there's two that are in development right now. We have Dragonfly, and actually, if you can go to that one chart that shows the Dragonfly spacecraft. I think that was chart 31. Yeah, and yeah, you see New Horizons with the RTG, but you see the Dragonfly octocopter. There's on that end just to the left, you see that cylinder. That's actually where what we call is an MMRTG. So it's a slightly different version of the RTG than what you're seeing on New Horizons. What it does is it has a slightly more efficient way of generating electricity from that differential in the heat, as Bethany was talking about before. So that's the Dragonfly spacecraft. And then there's also other missions that are under study. And Bethany alluded to the Trident mission. That's the one that's going to be going. If it gets selected, it'll go to Triton, the moon of Neptune. That would also be using an RTG. I'm not sure whether it's the MMRTG that we have here or the regular RTG, but that's another one. Plus, there's always concepts. Scientists and engineers, we're always working together to come up with new ideas and new places to explore. There's another mission that we're looking at called the Interstellar Probe that will actually leave our solar system, and that would require an RTG as well to power it.
Yeah, that Interstellar Probe mission is going to be interesting. What can you tell us about that?
So it's a study right now. So this is not a funded mission, but the thought is that if you're we live in a house, you live in a house or an apartment. If you wanted to study your house or your apartment, you might walk to the kitchen and walk to the bathroom and walk to your bedroom, and you understand everything about the inside of your house. But you still won't really understand your house until you step outside your house and look at it from the outside. So think of our heliosphere the same way. All of these wonderful places that we've talked about in terms of visiting, Titan, Triton, the moons of Uranus, these are all rooms in our house. They're different parts of our solar system. But if we really wanted to understand everything about how our solar system worked, we need to get outside of it, look at it from the outside and see it there, plus look at interstellar space from a vantage point of being outside of that solar system. So that's what Interstellar Probe is all about. We want to take our first intentional steps into interstellar space and learn what is there beyond. And because it's so far away, the sun looks like a star. Solar panels just won't work, and that's where we need the nuclear power to keep that spacecraft going.
That sounds like a really interesting proposal. So good luck on getting that funded, because
hope so. Yeah.
Really neat. So we've been talking about all these robotic spacecraft. So robotic spacecraft are just, as it sounds, robots that go without humans on board. Just a robot explorer to go do exploration before we send humans anywhere. And that's what you need to do. You need to gather the science and understand before you can send humans. So we have a couple of questions about human spaceflight. One is, how long will it be until NASA can send a person to Mars? And another is, how long would it take to travel beyond our solar system? And is that manageable in one person's life? So two different questions there. Either anyone want to take one of those?
Well, I'll jump in, and anybody else can jump in and help. So you're talking to a planetary scientist, an RTG manager, and an engineer who predominantly have worked on robotic spacecraft. So that is at least what I've been doing for 20 years. So I'm by no means an expert on human spaceflight. I haven't worked on any systems there, but it is our nation's plans to land people on Mars. We are hoping that we will use the moon as a stepping stone. There's a program called Artemis, which is in Greek mythology the sister of Apollo. If you remember back in the 60s, the Apollo missions were our first landings on the moon. We're trying to reclaim that magic with the Artemis program and go forward to the moon again, and restart our human exploration. Once we understand how the systems need to work to get us off this planet and land onto the moon, we'll use those technologies to move us forward to Mars. So this thing might happen in the next 20, 30 years or so. So these are the kinds of things that we'd love for you guys to participate in as you guys get older and start taking our jobs as time goes on.
Yeah, that's something that's definitely within your lifetime as a young person. Probably we haven't developed all the technology. Right now, it takes a while to get to Mars, and sure, you could be in a spacecraft with you and your closest friends for 8 or 9 months, but it would sure be better if we could go faster. So we are working on some of those advanced technologies as well. So go ahead.
Can I actually add on to Deepak's answer? A great part about the Artemis program is that it's going to include something called the Gateway, which is a lunar outpost that's going to be sitting around the moon. And it's going to support human and scientific exploration for further deep space. So it's critical to have this because it might serve for a future model for how we might get to Mars, right? Or a future landing post to Mars. So this is all small stepping stones to get those humans to Mars. It's not big stepping stones, right? But very, very cool stuff.
Yeah, for sure, for sure. And when we talk about sending these robotic probes beyond our solar system, we're talking years, right? This is not something that happens in a few months. So it's a number of years before we get a robotic spacecraft out there. That'd be a long time for a human to be sitting on a spacecraft.
Yeah.
All right, so we're going to shift gears. We have a lot of questions about your backgrounds, panelists, your educational backgrounds, your work backgrounds. So I'm going to start asking you questions, and I'd love for you each to chime in. And I'll pick one of you to start, and then each of you could pitch to one of our panelists. So the first question is, what did you study in school? And Kelsey, I'm going to go ahead and start with you.
Sure, yeah. I was interested in lots of different subjects. When I was in school, I didn't know for sure that I would become a planetary scientist. But so in middle school, in high school, I just did the best I could on all of my subjects. Believe it or not, we need every kind of person with all different kinds of skills to run a spacecraft mission. It might be obvious that you want to have engineers and scientists, but we also need artists and people who are really good at communication and relaying the science to the rest of the world. We need people who are good at finance. We basically need every type of skill set. So there's lots of different ways to work on a spacecraft mission in the future. I saw a question about that in the chat. But for me, in undergrad, I actually studied astronomy and anthropology. And then for graduate school, I switched more to the geology side. So for me, in my field of planetary science, I always think of planetary science as kind of halfway between geology and astronomy. And there's people who come to my area from all different sides. There's people who come from engineering because you need to know about how materials work. So there's lots of different ways, but that's how I got into it.
Cool, thanks. Deepak, you want to tell us what your academic background is like and how you got into your work?
So I agree with everything that Kelsey said. It's any background can find a way into space. No matter what you're doing, there's a place for you in space. My specific background was when I went to college, I studied electrical engineering, and specifically I studied communication systems. So how does your cell phone actually talk to the cell tower? That's the kind of stuff that I worked on and learned while I was in college. And then my first job was here, actually, at the Applied Physics Lab out of college. I hadn't even heard of APL before, and I just sent at the time, the internet was like a new thing, and like there was this posting online for something, and I just submitted a resume. It was a big thing. I'd never done that before. And they called me in for an interview, and they said, hey, how would you like to work on the communication system for a spacecraft that we're going to launch in a few years to go to Mercury? And I'm like, well, that's a little bit farther than a cell phone to a cell tower, but let's give that a shot. So that was how I got into space, was through the engineering door and just applying radio technology that would have been used here on Earth to a spacecraft that was called Messenger. And you guys can Google Messenger. It's a fantastic mission that orbited Mercury for a few years. And that's how I got the space bug. And I've been doing it for the last 20 years.
Wow, that's interesting. You got that job right out of college. That's super cool.
I was very lucky, very fortunate.
All right, Bethany, what's your academic background and how did you get to where you are today?
Yeah, so I started at just, undeclared in college, but I knew that I loved chemistry and I really liked math and seeing how all of that went together. And I also just happened to take an environmental science course as my freshman seminar type. And I loved that in environmental science, I was specifically interested in fuel and algae to fuel, making sure our dependence on fossil fuels wasn't as heavy. So I ended up continuing on and I did a whole research and all the way through my master's on saltwater algae tolerant to fuel potentials for avionics specifically. So that's how I tied environmental science and chemistry together. I was also very lucky that I grew up in the Cleveland area, and as I was applying to internships, I got selected to work at the NASA Glenn Research Center for a summer internship. And as I said, I was undeclared, and I was actually brought into the facilities group for engine research. So that's also how I tied together the environmental science, fuel, and engine research stuff, and I kind of carried that with me. So I knew after my first summer working at NASA, I knew that was where I wanted to be, right? You're encouraged to learn so much more about your environment. You get to see all the amazing research that's going on in all the different test facilities. And NASA already really encouraged you to find your own path and look at other areas at NASA that might be of interest to me in the future. So I held a couple different internships at NASA. I did one specifically in biofuels. I did one in nanomaterials research. And I loved it all. I loved the learning aspect. And, at the same time, I also don't want people to think that maybe because, they're working a different job right now, that this isn't open to them. Because while I was doing that, I was also, when I wasn't interning at NASA during the school year, I was working at an ice cream shop or an electronics store. So all of those experiences benefit us in different ways and how to interact with customers and stakeholders and just help you find your own path in the future. So once I had the internship, I knew that was it for me. That's where I wanted to work, and I followed that path. And I think anyone who's interested should look at it's intern.nasa.gov, and it's a one-stop shop for all of NASA's internships.
Yeah, thanks for that, Bethany. And interesting you bring up doing other jobs. My background, I have an undergraduate degree in mathematics and a master's degree in teaching and learning. I was a high school math teacher before I joined NASA, and I loved teaching math. It was a lot of fun, and then decided I should perhaps go get some experience in the real world that I could take back to the classroom. I ended up getting a PhD in environmental science, and I've worked at 3 different NASA centers. I worked at NASA Armstrong in California, NASA Johnson in Texas, and now JPL in California. And so I work in the education office, and my job is changing some of the science and engineering we're doing into lessons for the classroom. So there's just, as our panelists said, lots of opportunities for working at NASA in a variety of different career fields. Another question from Huda Akbari from San Diego, California. What is your daily life like at NASA? And Kelsey, we're going to go ahead and start with you again.
Cool. Yeah. Great question. So I, as I mentioned, do a couple of different jobs. I work partly on planning what the spacecraft will do next. And so that involves basically a lot of discussions amongst the team about what's the best kind of science we want to get. And then we go ahead and actually say we're going to do this science. And then that initiates a series of steps to get the information to the spacecraft. So there's programming. People program what's going to go to the spacecraft to tell the spacecraft, okay, we're going to turn this way and take this picture. We're going to turn this way and take this other kind of composition data. And then eventually that signal does get sent from Earth to the spacecraft. And the spacecraft takes the observation, sends it back to us eventually. And then the second part of my job is that I get to actually work with the data. And in my case, I look at a lot of pictures, just like what you're looking at here, of these moons. And what we do is we say, okay, for example, on Ariel there, you see those fractures looking, line looking things, but there's also some smooth areas. And that's just a really basic example of the kinds of things we do to say, okay, what would have created the lines? Well, we think that's some kind of tectonic feature. So then I go ahead and do some mathematical modeling to see if that would actually create what we see on the surface. Same thing with the smooth areas. One idea we have for that is that those are actually icy volcanic eruptions. And so we also would say, okay, let's try to create a model and see if we can reproduce what we see on the surface. So I look at pretty pictures, which is great, but I also do a lot of modeling to say, can we recreate what we see?
And it sounds like you work with others too a lot. So interacting.
Definitely. It's super collaborative. I'm constantly talking to people about all their cool ideas, and you need lots of different ideas to really do this well.
Yeah, diverse viewpoints are really important. People coming from all different backgrounds and experiences.
Oh, totally.
Yeah, for sure. So Deepak, what does a day look like for you?
I think you guys kind of touched on it at the very end of Kelsey's discussion here, was just it's teamwork. My days, so I'm an engineer, and when I'm doing work, it tends to be building these things that people like Kelsey get to operate and get these pretty pictures with. So here's an example of a module that I actually built that'll be flying on Europa Clipper. There's little wires on here that are about tiny wire. You can't see it. You have to like magnify a lot, but the wires here are about the size of one of your human skin cells, the width of it. And as Kelsey was saying, they send up commands to the spacecraft. The spacecraft will do its thing and then send the information back. Well, all of that data gets sent when we go to Europa. Will be sent over one of these little itty bitty wires that are the size of a human skin cell. Don't worry, it'll still work. It's tiny, but it works. So that's down on the engineering side. That's just one example of the kinds of things that I build. Now, when I say I build, it's really we build, because I don't actually build the thing myself. It's a large team of people, a huge team of people, and pretty much my days these days are spent in meeting after meeting after meeting, working with these people to make sure that we're all doing the same thing and working towards a common goal. And just to give you an idea about how large these teams are, you have teams of teams of teams. Now, Kelsey, I don't think I've ever met in person, and she's working on New Horizons, which is something that I spent about 4 years of my life working on a decade ago. And I'm really happy that we got paired together on this panel, because
totally,
it tells you the broad scope of these teams. There's hundreds and hundreds of people working on these missions, possibly even thousands and thousands, that you just got to hand things off, and you have to communicate very well. And that's why these teams and the team dynamics are really important to being successful.
Yeah, it's interesting that you point out that a lot of us have never met, even though we're all working on some of the same projects and we're clearly in the same country, but we even have international collaborations. And sometimes we get to meet our international colleagues in person. A lot of times it's remote, but yeah, lots of collaboration. Cool. So Bethany, what does a day in the life of Bethany look like?
Well, a day in the life of Bethany is a lot of coordination from a lot of different players, as Kelsey and Deepak have already said. So to obtain launch authorization for a mission is a several-year process, right? They don't just let you throw it on the pad and launch it off. So, for Dragonfly, we're already looking at that launch authorization process and getting everything in place to make sure that we have all of our review boards ready and all of the studies and products that we need ready to meet that 2027 launch authorization date, right? So this is starting almost 6 years in advance. So that's a lot of coordination with different players, such as the actual Dragonfly mission and lead, and NASA lead and APL lead, Zibby Turtle, NASA headquarters environmental policy group, as well as the Office of Safety and Mission Assurance. We work with JPL's Launch Approving Engineering Office a lot to make sure that we're getting the correct studies done to meet our reviews for launch authorization. And I also work across federal agencies to look for synergies in this launch authorization process, right? So we're not the only ones who have requirements, we work with the Air Force, and sometimes we use their ranges to launch things off. So we have to make sure that we're all understanding what the requirements are for launch authorization. So a lot of coordination and making sure all of our ducks in a row. And there's a lot of ducks to get put in a row. And then finally, I also participate in NASA Glenn Research Center's Rocket University program, which is a technical development program to experience the entire life cycle of a project. And with that, I'm working with a small team to solve alternatives for surviving the lunar night, which has very extreme heat ranges, right? So right now we're using radioisotope power systems to help survive that, but are there other ways that we can do it as well?
So that's really interesting. There's all kinds of stuff going on. And as you're gathering from our panelists, we have folks who come up with the idea for a mission. We have folks who are building the hardware that's going to eventually fly. We have folks figuring out how to launch that hardware and getting all the clearances for that. And then we have the scientists who benefit from all the people who did all that other work and get the data back from the mission. So lots of stuff going on. We have another question here about careers, and it's from Pavel Pavlov and Valentin Nikolov in Sofia, Bulgaria. How can I become a NASA scientist, and what should I study as a specialty? Who would like to take that? Kelsey?
Sure. Yeah, I'll just say hi in Bulgaria. Actually, my very best friend is from Bulgaria, so I've been to Sofia a few times, and I had a very nice time there. So, we've kind of hinted at this, but there's just lots of different ways. Of course, you want to try to get some programming and math and a general science background, and even maybe a general engineering background if that's available to you. But all those basic things, basic chemistry, basic physics, even biology, like as Bethany was talking about, all of those backgrounds are super helpful and will lead you to keep working and finding what you really like. And I would say, go ahead and pursue which parts of that you really like. And don't worry about having all of the pieces. There's no way to have none of us have all of the pieces. We have some pieces that we're kind of good at. We have other pieces that we're really good at. And all that comes together to make you someone who can work on a spacecraft mission.
All right, great, thank you. Another question from one of our winners, Erin Heisel in Hello, Montana. What was it like, or what is it like, for NASA to work for NASA during the COVID-19 pandemic, and how did that affect progress on space exploration and development? Obviously, you can probably tell a lot of us are working remotely. Anyone want to take that? Deepak?
I'll jump in really quick. So there's a guy by the name of Johann Kepler that came up with the equations of motion for how planets move. So, we know exactly how these planets move, and there's equations with, lots of variables that describe it. None of those variables account for infectious diseases. So no matter what's going on here on Earth, these planets are moving, right? And as we mentioned before, we went to Pluto via Jupiter. We have missions that are en route or going to be launching soon to go to various asteroids or to go to Dragonfly, to Titan. These schedules have to be maintained because it's not like driving to the grocery store where if you leave at 2 o'clock or leave at 2:10 or you leave at 4 o'clock, it's the same thing. It's no big deal. For us to get from one planet to another planet, you have to launch right when the planets are literally in the right alignment so you can fly by them just ever so precisely to get to your targets. And that's why you hear these terms launch windows and launch periods. You can only launch at specific times, and sometimes these times are years or months or even years apart. So yeah, there's a pandemic going on, but you just got to tough it up and work through it. So right now, one of the things that we're doing here at APL is that, likely it's getting a little bit easier these days, but in the earlier parts of the pandemic, we had to come up with processes to allow people to still work on site because you can't build a spacecraft virtually. Right, you can do a lot of things virtually, and we're learning how to do more and more things virtually. But certain things, like building this, people needed to be in there and touching it. So we had to limit access. Those of us that didn't need to be there stayed away to keep the people that had to be there safe as they could. And we just pulled it off as a team, and we're still on schedule for all of our upcoming launches. Now, what has happened is that some of the future launches that haven't been planned out as close yet, some of those have gotten pushed out a little bit to enable us to make sure the launches that are really close and upcoming can happen. So, we do the best we can with balancing multiple priorities.
Yeah, there was a fair bit of juggling going on for even getting the Perseverance mission launched, which launched in the first part of the pandemic. The spacecraft was built and ready to go, but we had to do some integration over at Kennedy Space Center, and just taking all the protocols that you all are familiar with, wearing masks, hand washing, all that good stuff, and then, as Deepak mentioned, folks like me, I haven't been on lab at JPL since March of 2020. Because my job doesn't require me to be there, and I needed to leave room for the people who are building hardware to be in there because they have to be there. And I had to figure out how to do my job remotely, which it's a challenge, but it's worked. So that's really, really cool. Any other comments on that from others?
I just want to comment that just like a lot of you that had to go to probably virtual school, right, that we all had to deal with that as well. And there were definitely some struggles in the beginning, but I think everybody really pushed through, and it was wonderful to see the team come together to make sure that we could still get the required people in there to build the hardware and help them move and to have processes so that we didn't slow down. So it's definitely been different. It's not as easy, you can't just pop your head into somebody's cubicle and ask a quick question. So you're now having to schedule the meetings, but it's also given us all a lot more time, to spend with our families too. So like I've got a 2-year-old daughter at home, and it's been fun to see her exposed to all this NASA language at such a young age. So it's offering some unique experiences in that way too.
That's really important too, to point out that some of us have had more opportunity to spend some time with our families if we're not commuting, and that's been great. Speaking of kids, obviously our audience here are students, elementary school, middle school, high school. So I'd like each of our panelists to tell what were you like in, pick a grade, upper elementary, middle, or high school, and what were you thinking about science? What got you interested in the science or engineering? Was there anything in your young life that you were doing that especially you found now prepared you for what you're doing? Was there something that you never were even thinking that was going to be a good skill, but now you have it because you did it when you were younger? So who'd like to start? Deepak?
I was going to say, Deepak, go for it.
Okay. So the thing that I loved doing from elementary school all the way through high school and afterwards is music. So I still play to this day the trumpet. I'm in the Hopkins Symphony Orchestra. I play classical music. I've also played jazz, and I like composing music, and I like playing music with my daughters. I got three girls, and for me, that was what kept me going through elementary school, through college, and through now. But what I really credit music with for what I think my success is that at a very young age, I was already performing in front of people. So I'd get on stage and I'd play Yankee Doodle or something like that on my trumpet. And, ever since 3rd or 4th grade, I'd been used to being in front of people all staring at me. Now, I shudder to think of how I sounded playing Yankee Doodle as a 3rd grader, but I got used to communicating with folks. And one of the things that we touched on here was that to be successful, to have a successful mission, you have to communicate, and you have to work well in teams, and you can't be shy. You need to be comfortable talking to anybody. And that's where I think my music background really helped me develop those skills very early on. So that was my hobby back in the day. and still remains to this day now.
Also develop some math skills, I think, as well, right?
That's right. That's right. There's a lot of analytical stuff going on as you're playing. You're right.
Cool. All right, Kelsey.
Sure. Yeah. No, it's hard to top that. That's a great story, Deepak. And I would just say that I didn't know what I wanted to do. So it's not like I always knew for sure this was going to be the path. And as Ota was saying, there's so many things that you learn that are going to help you in the future. I would say that I did try to work very hard in general. And I tried to get good grades and when I was in middle school and in high school. And being on a spacecraft mission is a lot of work, but it's also really exciting. I would say maybe the turning point for my decision was I got really interested in astrobiology. I like the idea, like some of you guys already brought up, about having oceans in some of these distant worlds in the outer solar system. And so I think that's what really kind of said, okay, I really like this subject. I like a lot of subjects, but I really like astrobiology, so I'm going to try to pursue that. And that reminds me that we've been talking about how everyone has these varied career paths, and I also help maintain a blog called the Women in Planetary Science blog, and it's not just for women, but we do feature the career paths of people who have become planetary scientists or people who work on spacecraft missions, and we have a number of different interviews with people talking about exactly this. How did they become a planetary scientist? So you can check that out as well.
Cool. Yeah, I had no idea when I was a kid what I wanted to do when I grew up. I mean, I had all kinds of ideas, but it's not what I'm doing now. So yeah, lots of experiences. Learn everything you can. Bethany, what were you like as a kid, and did you have anything that gave you an advantage in your current job?
So as a kid, when you said that story, the first thing that came to mind was when I was in third grade, I got in trouble for reading ahead in my third grade science textbook, right? So whatever the homework assignment was, I kept going. So I've always had that interest in science. And I've always known that is just what I've liked. A lot of gardening as a kid and watching Bill Nye the Science Guy, just interest in science in general. But something that I think that's always helped me is that I get out of my comfort zone, or I force myself to get out of my comfort zone. And I think that that's never easy for anyone. But when I was applying for my NASA internships, I remember I was encouraging some people, that I went to school with to apply to, and they would just say, oh, no, I'm not qualified for that. And you think I am? I'm also in college with the same classes that you've taken. So have confidence in yourself. We know that you're applying for an internship. We know you're not going to know everything and how to do everything in the internship that you're applying for. That's a part of the development process. So go ahead and apply to what you're interested in, and take those opportunities when they're presented to you. So when I got the opportunity to work on the piezoelectric nanowire synthesis, I tell you, I didn't know anything about that, but the opportunity came. So I took it, and then I learned a whole new field of science that did help broaden my horizons, but I also decided that maybe that wasn't the whole career path for me. But I met valuable career networks. I learned a whole different side of NASA that helps me every day in my current work to understand how these different offices work. So go ahead and broaden your horizons, take opportunities that are presented to you, and don't doubt yourself. Go ahead and apply. And if you don't meet the criteria, they won't select you. And that's the worst that happens. And if you do meet the criteria, you get a whole career out of it, like I did working for NASA. So I tell you, I didn't feel qualified when I first applied for my first NASA internship, and here I am today.
Great, thank you. And I think one of the things that has been kind of a thread through all of your answers is being a lifelong learner. So a lot of times in school, we feel like we have to get the right answer, so we get the A on the test or whatever. But truly, knowledge changes. What we know about science, everything kind of changes and evolves. And so it's better for you to learn how to think critically, how to analyze data, how to continue learning, because I don't think any of us are doing exactly what we went to college for. We may have things that we learned in college that we're applying for sure, but maybe we have learned a whole lot of other stuff that is helping us, and we have to do that along the way. And we're nearing the end of our time. I want to answer one more question. One of the questions that came in was, when is the youngest you can be an intern at NASA? Most of our interns are university level, and you would be a science, technology, engineering, or mathematics major. And it's usually after you have a year of college under your belt. But some of the NASA centers occasionally will have a high school program. So it's usually age 16 and up. You'll have to look around at the individual NASA centers for that, because those are kind of hit or miss, but they are occasionally out there. So with that, I would encourage you to apply to be an intern with us, and when you're of age, and also to continue your learning about the Scientist for a Day targets this year, and keep your eyes out for other essay contests that NASA has. And we hope that you will enlighten us with your visions in the future for other targets. So thanks again for tuning in with us today, and thanks for all of you who entered the contest. Have a good rest of your day. Bye-bye.